Hello, linear algebra student. This video is for chapter 5.3. I'm going to do two examples, actually three examples of diagonalizing a 2 by 2 matrix or two 2 by 2 matrix and also a 3 by 3 matrix. This is the steps that we covered last time. So to do that, we find all the eigenvalue and we find, if possible, n linear independent eigenvector for each lambda. And then create P, you go to those eigenvectors, and D, you go to the corresponding eigenvalues and do checking. First, so these are the 2 by 2 one. I did not give eigenvalue, so I have to find eigenvalue first. To find eigenvalue, we would have to solve a characteristic equation, which is determinant of 3 minus lambda -1, 0, 3 minus lambda equal to 0. Actually, as a matter of fact, this is a lower triangular matrix. So we actually can it's a triangular matrix. So we can just say 3 actually is the eigenvalue. But for the purpose of showing an example, I would say -0 equal to 0. That means lambda equal to 3 is the eigenvalue. So what's the eigenvector then? To do that, find eigenvector. We would have to solve the equation of a minus 3i x equal to 0. Solve for this vector x. So that a minus 3i is equal to 0. That would means a equal to 3x, right? So so a minus 3, so that means it would be all the diagonal minus 3. So we have 0, -1, 0, 0, x equal to 0. I do an augmented matrix of 0, -1, 0, 0, 0, 0. RLEF would become 0, 1, 0, 0, 0, 0, because I can just do it myself. Scaling it, that means x1 is free. x2 is, this is the previous position, second variable, the free variable. This is the variable that is equal to 0. So our eigenvector is only 1, which is 1, 0. And there is this one, but this one is it only have one eigenvalue, so 1, 0 cannot span. R2, right? I don't have another one, so there's A is not diagonalizable. So A is not diagonalized. You cannot find all two columns. At least you have two columns of eigenvector. So otherwise, it's not. Okay. The second one, I'm going to leave some space to do the second one. So the column matrix A is 4, 2, -3, -1. We want to find eigenvalues and eigenvector to create P and D so that we can diagonalize A. So to find eigenvalues first, we solve the characteristic equation determinant of 4 minus lambda, -3, 2, -1 minus lambda is equal to 0. That means 4 minus lambda times -1 minus lambda minus a -6 is equal to 0. It's 2 by 2, right? AD minus BC. So this multiply it out would be -4 minus 4 lambda plus lambda square plus 6 equal to 0. And simplify it will be lambda square minus 3 lambda plus 2 equal to 0. Factor it will be lambda minus 1, lambda minus 2 equal to 0, meaning lambda is 1 and 2. We have two eigenvalue. Let's do lambda equal to 1 first. When lambda equal to 1, we will have to solve a minus 1i x equal to 0. Right? So all the diagonal minus 1, so it'll be 3, -3, 2, minus 2, x1, x2 equals 0. It's a homogeneous equation, -3, -3, 0, 2, -2, 0. And you can do the RREF. Would be, I think you can just do it by hand, but I put it in decimal just to make sure. Oh, it's A. 1, negative 1, 0. Because if you can get rid of these the second row by 1, negative 1. Oh, this is a plus 3. 1, negative 1, 0, 0, 0, 0. So that means x1 is equal to x2 and x2 is free. So my v1 would be equal to what? 1, 1, right? x1 and x2 are the same. For lambda equal to, what is the other one? 2, we would have to solve a minus 2I, x is equal to 0, exactly like what we did in 5.2. Minus 2, so be 2, negative 3, 2, minus 2, negative 1 minus negative 3, x is equal to 0. Have to solve this. So it means we would use the augmented matrix of 2, negative 3, 0, 2, negative 3, 0. You can see that the second one get cancel out. So you can do RLEF, or you can just solve it or just REF. So it'll be 1, negative 3 over 2, 0, 0, 0, 0. I did do it in here. So B, negative 3 over 2, right? So x1 is 3 over 2 x2. x2 is free. So our v2 would be what? If I assign x2 equal to 2, then v1 equal to 3. So we would have, we use the space over here, would have p equal to the 2 eigenvector, 1, 1, 3, 2. Our D would be the diagonal of the eigenvalue 1 and 2, 1, 0, 0, 2. So let's check AP. AP is 4, negative 3, 2, negative 1, and then P is 1, 3, 1, 2. This is the one that is harder to multiply. So before minus 3, multiply this 2, 12 minus 6. 2, 1, 1 is 2 minus 1, 2, 6 minus 2 equal to 1, 6, 1, 4. And if I do dp, no, pd, okay, pd, then it will be 1, 1, 3, 2. D is 1, 0, 0, 2. So you will see that this minus this multiply this is 1, this multiply this is 6, this multiply this is 1, this multiply is 6. So they are equal, right? AP equal to PD. So that means A is equal to PDP inverse. And we diagonalize it. Let's do the 3 by 3. So I have, this is actually the one that we did earlier, the last videos when we actually given to us as P and D. So we'll just show how we can find them. So because of a 3 by 3, it's harder to find eigenvalues unless you use a calculator. So most of the questions you get would be provided with a lambda. So let's do lambda equal to 2 and figure out the eigenvector. So that means solve, just like the first two example, a minus 2I x equal to 0. So you would have to do an augmented matrix of negative 2, negative 1, negative 3, 0. I skip a step. 2, so minus 2, so become 1, 3, 0. Negative 2, 1. This would be minus 2. 1 minus 2 is negative 1, 0. So do the augmented matrix and RREF in the calculator. Most of them you can actually do it by hand. So I have negative 2, negative 1, negative 3, 2, 1, 3, negative 2, 1, negative 1, and I RLEF C. Okay. This would become 0, 1, 1, 0, 1, 0. You can see that these two are actually the same thing, so you can write this out. So the only one that's left over is this, 0, 1, 1, 0. and then 0, 0, 0, 0. So, so that means x1 is equal to negative x3. x2 is also equal to negative x3. x3 is equal to x3. So v1 would equal to negative 1, negative 1, 1. Right? So then we would do r equal to lambda equal to negative 2, which is to solve a plus 2i x. So my mental matrix becomes, I would add 2, right? Add 2. So be 2, negative 1, negative 3, 0. 2, add 2 become 5, 3, 0. Negative 2, 1 become 3. So these two are actually dependent of each other. So only have 2, so that we have a non-trivial solution. But anyway, do an RREF with the calculator, with the decimal calculator. I input into D2, negative 1, negative 3, 2, 5, 3, negative 2, 1, 3. And when I do RREF of D, become what? 1, 0, negative 1, 0, 1, 1. So very similar to what we have. 1, 0, negative 1, 0, 0, 1, 1, 0, 0, 0, 0, 0. x1 equal to x3, x2 equal to negative x3, x3 equal to x3. So v2 would equal to 1, negative 1, 1. Okay, so far so good. The last one, lambda equal to 4. So you can see that it is kind of repetitive now. You have to solve a minus 4ix equal to 0. I would use the augmented matrix of minus 4 in all of these. So be negative 4, negative 1, negative 3, 0, 2, negative 1, 3, 0, negative 2, 1, 1 minus 4, 1 minus 4 is negative 3. See, these two are dependent, so there is a non-trivial solution. So I put it in here for negative 4, negative 1, negative 3, 2, negative 1, 3, negative 2, 1, negative 2, 1, negative 3. So I'm going to do RLEF of E, because that is E, is 1, 0, 1, 0, 1, 0, 1, 0. What is the second one? 0, 1, negative 1, 0, 0, 0, 0, 0. So RLEF. That means x1 is equal to negative x3 again, but x2 is equal to x3. x3 is still 3. So my v3 would be equal to what? Negative 1, 1, 1, because 2 and 3 are the same. So now I get 3 matrices of 3 vectors. So my P would be this one, negative 1, negative 1, 1, 1, negative 1, 1, negative 1, 1, 1. Okay. They should be linear independent because they are from different eigenvalues. And then my D would be the eigenvalues 2, negative 2, and 4. 2, 0, 0, 0, negative 2, 0, 0, 0, 4. So I should do an AP. I should do a checking of AP and PD, but I actually did it already here, right? AP, this is what I got, negative 2, 2, 4, 1, negative 1, negative 1. Yeah. So this is just to confirm that I did. And if you want to, you can check AP is equal to DP. Because both of them, according to the last example, in the last video, I have it negative 2, negative 2, negative 4. Yeah. I think I did actually multiply. Did I? No, I did not. Yeah, but can just copy from previous and they should be the same. So this shows us that A is PDP inverse. I'll do another example in the next video.